Hi again, this is another video on blockchain security, and in this case it's the second one of the smart contract security series. And at this stage we're actually ready to look at some code and the particular vulnerability. And I thought we should start off with the reentrancy vulnerability, because that's a very good example of an easily explained vulnerability that keeps occurring. It's one of the first big vulnerabilities that caused a large incidents back in 2016. And it still keeps popping up again and again. So it's a very important vulnerability to be aware of. So here's actually a snippet of code, that's sort of the minimal example of this vulnerability in a very simplified smart contract. And this smart contract here maintains a mapping between an address and a balance. The assumption here is that the contract actually holds some ether, and the balances of different users are managed here. This is quite a common use case for something like investment funds or vault contracts. People set their money to this contract, and there's a certain amount is assigned to them. And obviously there's a payout function which allows the owner to withdraw their funds. The owner of the funds, not the owner of the contract. And this is done here. When payout is called in a transaction, the transaction origin, the message sender, sends himself the balance assigned to him. And this is done by this call value function, which specifies the amount. And what we can see is we first transfer the funds and then we set the balance to 0. Now, anyone that's familiar with sort of concurrency issues and race conditions will see that there's a problem here, in that there is a moment in time when the balance is not what it should be. And if code can be called, or this function can be called again within this time frame, then there's an inconsistency there that can lead to problems. And this can actually be exploited due to the fact that the message sender might not be an external wallet or an external account. It can actually be a smart contract. And in this case, this call value invocation here, this actually executes the fallback function of that smart contract, which can implement any piece of code. And one thing a malicious actor might do in the fallback function, which is meant to deal with receiving ether, but one thing an adversary might do is to call payout again. And of course, when payout is called again recursively, the actual balance has not been set to 0 yet. So this can actually be repeated until the whole ether balance of the contract has been drained. And this means you can actually withdraw other people's funds, which is obviously not the desired effect. And this is quite common, but it's easily avoided. And let's just see how it can be avoided. Now, the first thing we can do, and I consider this to sort of be a quick fix, but not a real fix, it's a workaround, is to use a gas limited function instead of call. And you can actually make transfers with transfer or send, and these are limited to 2,300 gas. And this just means that the gas that is forwarded in this function to the caller is not enough to do much more than just receive ether. So if the contract tried to do something else, like calling payout again in our case, it would just run out of gas and fail. Now, I consider this a poor solution and a bit of a workaround. Also, I do think the transfer function is a nicer syntax and should be used instead of call for transferring ether. I think it's just a workaround in this case. because it doesn't solve the underlying problem. Now, there's two issues with this. There might actually be reasonable things that have to be done, or there might be valid uses for a fallback function that actually does more than just store a little bit of ether. Maybe keep some do some additional bookkeeping, do something else. There are valid use cases that might just run out of gas that are not possible. And in that case, it does make sense to use call instead of transfer. And another issue here is that the gas limit might actually change in future version of the protocols. And we almost saw this happen in the Constantinople update earlier this year, where a protocol update had to be postponed because someone realized that the reduction of gas in some cases would cause a reentrancy problem for already deployed contracts. So you cannot trust the fact that the gas limits will always remain the same. It's better to find a proper solution. And the cardinal rule for this is to not change state after external calls. Now, that's really the clean way of doing it. Just do the balance change before you actually make the transfer. There's no harm in that. And that actually leads to a pattern which is called checks, effects, interactions pattern, which means before you do something, you check every assertion, or you put insertions or that actually check if the action should take place. For example, if the user has enough balance that he is allowed to call this function, all these things should come first. Then you do the effects it has on the state. You update the state, and then you actually do the interaction, well, the actual transfer in this case. So it's a way of ordering things that is much more secure than other solutions, and it's really best practice. So just an interesting fact on the reentrancy issue. There's a bit of history here. In 2016, we had the DAO attack, and I encourage anyone to read up on this if you haven't if you're not aware of it. But that was sort of a big moment in smart contract security when we became aware of how badly things could go wrong. So the DAO was sort of a crowd-funded investment fund where people put their money into a smart contract and then voted on what the money should be spent on, in terms of startup funding in this case. And DAO just means decentralized autonomous organization, which is an interesting concept in itself, because it's sort of a company run autonomously on the blockchain. But the DAO was one particular DAO, and it had this issue. So, as I said, it was a crowdsourced fund, and it was much more successful at first than expected, and suddenly there were 12.7 million ether locked into a single contract address, which is always dangerous. And that at the time was estimated to be $150 million US dollars. And it was 15% of the existing ether at the time, which is quite a big impact on the ecosystem. So the attack happened on 17th of June 2016. And basically what happened, the DAO had a way of recovering funds. If you're not happy with the way the DAO was run, you could create your own child DAO, and your funds were diverted into that. And for safety or security, there was a 20-day locking period before these funds could be used. And of course, there was this reentrancy vulnerability, and what happened was that someone managed to put much more funds than he actually owned or were assigned to him or paid in by him into a child DAO. And when the community realized this, there were 28 days to recover the fund or look at the problem and find a solution. And of course, that's not very easy, because the attacker really just followed the rules of the smart contract, even if these rules were written down accidentally. And there was a big discussion whether code is law in this sense, and it should be allowed to go ahead, or if the state of the actual blockchain should be changed. And that caused a split in the community and a hard fork in Ethereum. And Ethereum Classic was born, which is actually a blockchain that follows the earlier history of Ethereum, where the DAO attack was allowed to happen. And in what we know as Ethereum now, they actually rolled back these and protected these funds. And of course, the Ether price crashed temporarily, and that so we now know that is something we recovered from quickly, and the DAO itself collapsed. But obviously the impact was huge, and for me it's interesting that even last year there were big cases with reentrancy issues still there. So people don't seem to have learned that much from this early big incident. But anyway, I end this slide as this video as I end all videos, encouraging people to get audited, and in this case, of course, get your smart contracts audited. Very important. That's all for now. In the next video, we'll probably look at overflow issues and then on some other vulnerabilities.